Right now, without you knowing it, something is tearing through your body. Not bacteria, not radiation from your phone. Something that originated at the violent death of a star that exploded before the Earth even existed. These particles are moving so close to the speed of light that if light were a car doing highway speed, these particles would be in the next lane. They pass through the walls of your house, through your skin, through your organs, through the atoms that make you, you. And there is nothing you can do about it, because this has been happening every single second of every single day of your entire life. Welcome to space, the place we've been staring up at our whole lives. The thing we put on posters and use as a metaphor for wonder and adventure. Except we've been sold a lie. Or maybe not a lie exactly. More like a very comfortable version of the truth. Because the full truth about what's out there is something most science communicators tiptoe around. Not because it isn't real, but because once you really understand it, you can't unhear it. You clicked on the right video. What you're about to hear isn't speculation or science fiction dressed up as fact. Every single thing in this script comes from peer-reviewed research, NASA mission data, and findings published in journals like Nature, the Astrophysical Journal, and physical review letters. We're not going to talk about what might be scary. We're going to talk about what already is. Here's what nobody tells you. Space isn't just dangerous. It isn't just cold or empty or far away. Space is actively, structurally, fundamentally hostile to the existence of life in ways that go far beyond anything you've been taught. And the more we learn, the worse it gets. Because every new discovery we make doesn't just reveal a new danger. It reveals that the danger has always been there, quietly surrounding us, and we had no idea. Your entire existence happens inside an impossibly thin bubble. The atmosphere that keeps you alive is about as thick, relative to the size of the Earth, as the skin on an apple. Step outside that skin, and space doesn't just threaten you. It begins erasing you. And what's out there waiting in that darkness isn't just nothing. It's something far more unsettling than nothing could ever be. This isn't a video about astronomy. This is a video about what it actually means to be alive in a universe that never asked you to be here. But here's what's going to keep you watching. Because the terror of space doesn't just live out there in the dark between galaxies. Some of it is already headed our way. And one discovery in particular, which scientists confirmed in the last decade, should have made worldwide headlines. It didn't. We're going to talk about that. And when we do, you're going to understand why the researchers who found it spent weeks not sleeping. Chapter 1. The void that eats you alive. Let's start with the most obvious danger, because we've all heard about it, and almost nobody actually understands how bad it is. Vacuum. We know that space is a vacuum. We've been told that since we were children. But we treat it the way we treat the word cold when describing the Arctic. Sure, the Arctic is cold, but cold enough to freeze exposed skin solid in under a minute. Cold enough to kill a healthy adult in less than an hour. There's knowing something, and then there's feeling the weight of it. So let's feel the weight of vacuum. The air pressure at sea level on Earth is about 101,000 pascals. That's the force of the atmosphere pressing down on every square inch of your body. You don't feel it because your body pushes back with equal force, so you're in equilibrium. Now, in space, the atmospheric pressure drops to essentially zero. Not low. Not reduced. Zero. And what happens to your body isn't like slowly running out of air. It's more catastrophic than that. Your blood, which operates under that same pressure equilibrium, would begin to boil. Not because space is hot. Because the boiling point of a liquid drops as pressure drops, and with zero pressure around it, the dissolved gases in your blood would come out of solution the same way bubbles appear in a soda can when you crack it open. Imagine your entire circulatory system becoming carbonated. Now imagine that in your veins and your lungs and your brain. This is called ebulism. And it would render you unconscious in about 15 seconds. Not a comfortable 15 seconds. The kind where every soft tissue in your body swells to roughly twice its normal size because the fluids inside you are trying to become vapor and there's nothing stopping them. You would be dead in about 90 seconds. Not slowly. Not with time to think about it. 90 seconds. That's roughly how long it takes to brew a cup of tea. But here's the part that goes from dangerous to genuinely surreal. That same vacuum isn't just deadly to life. It's the dominant state of the universe. Think about this. All the planets, all the stars, all the galaxies, all the nebulae and clusters and everything we've ever photographed. Add all of it together. Every atom of hydrogen and oxygen and iron and carbon. All of it combined represents less than 5% of what the universe contains. The rest, more than 95% of the cosmic content, is either dark matter or dark energy, which aren't matter and energy in any way we understand. Which means the universe is, by overwhelming majority, made of things that are not things. The emptiness of space isn't an absence, it's the substance. We're the weird exception. And within that emptiness, the distances involved aren't just big. They break every intuition you have about scale. The nearest star to our Sun is Proxima Centauri, sitting about 4.24 light-years away. A light-year is the distance light travels in a year, covering roughly 9.46 trillion kilometers. So Proxima Centauri is about 40 trillion kilometers from Earth. If you got on a commercial airplane right now, a standard passenger jet cruising at 900 kilometers per hour, and flew toward Proxima Centauri without stopping, without ever landing, without ever running out of fuel, you would arrive in approximately 5.1 million years. Humanity's oldest recognizable ancestors, the ones we might actually call human, appeared on this planet about 300,000 years ago. So you would need to travel for 17 times the entire history of our species just to reach the nearest star. And that's the nearest one. Our galaxy, the Milky Way, is about 100,000 light-years across. On the same airplane, crossing our own galaxy would take 120 billion years. The universe itself is only about 13.8 billion years old. You'd need more than 8 ages of the entire universe just to cross our single galaxy at airplane speed. These numbers aren't here to impress you. They're here because they reveal something that most people never quite confront. If anything went wrong out there, if a ship broke down, if a colony failed, if a signal was sent asking for help, the distances mean help could never come. There's no cavalry in the universe. There's no rescue mission that arrives in time. Out there, beyond our little bubble, survival is a problem you solve with what you brought, because nothing and no one is coming from anywhere else. But the emptiness and the vacuum are almost quaint compared to what lives inside the emptiness. Chapter 2. The invisible rain that never stops. Go back to that opening image. Something passing through your body right now. Cosmic rays. The name sounds almost gentle. A ray of something cosmic. It sounds like a spa treatment or a yoga pose. The reality is that cosmic rays are some of the highest energy particles in the known universe, and they bombard the surface of the Earth continuously, every single day, every single hour, without pause. Here's what cosmic rays actually are. They're not light. They're not heat. They're subatomic particles, mostly protons and atomic nuclei, that have been accelerated to near the speed of light by some of the most violent events in the cosmos. Exploding stars. Collisions between neutron stars. The screaming jets of plasma that launch out of supermassive black holes at the centers of galaxies. These events act like nature's particle accelerators, flinging matter across intergalactic space at energies that dwarf anything we can produce in our most powerful labs by a factor that's hard to even state cleanly. The Large Hadron Collider at CERN, which is the most powerful particle accelerator humans have ever built, accelerates protons to energies of about 14 TeV, which stands for tera-electron volts. The most energetic cosmic ray ever detected, which slammed into our atmosphere over Utah in 1991 and was recorded by the Fly's Eye Cosmic Ray Detector, carried an energy of about 300 quintillion electron volts. That's roughly 3 times 10 to the power of 20 electron volts. To put that in a form your nervous system can process, that single subatomic particle, smaller than an atom, carried the kinetic energy of a baseball thrown at about 90 kilometers per hour. One particle, the size of nothing, with the energy of a thrown baseball. Scientists called it the "oh my god" particle. That was the actual reaction in the room when the data came in. Now here's the thing. Most of the cosmic rays hitting Earth are lower energy than that. They interact with our upper atmosphere and produce cascades of secondary particles that rain down on the surface. But our atmosphere acts as a shield, absorbing most of the danger before it reaches us. By the time the cascade reaches the ground, it's been substantially diluted and degraded. You're exposed to a low but constant background of cosmic radiation right now, and your DNA repair mechanisms are good enough to handle it most of the time. But astronauts on the International Space Station are outside much of that shielding. They receive radiation doses during a 6-month mission equivalent to roughly a lifetime's worth of medical X-rays, all compressed into 6 months. And that's with the Earth's magnetic field still providing some protection at the altitude of the ISS, which orbits at about 400 kilometers above the surface. Something roughly the height above Earth as the distance from New York City to Philadelphia. Venture beyond that magnetic shield into deep space, and the situation becomes significantly uglier. Astronauts on a Mars mission would face radiation exposure estimates that exceed safe career limits for NASA astronauts currently, and that's before accounting for the random possibility of a solar energetic particle event, which is when the sun suddenly erupts and floods interplanetary space with radiation spikes powerful enough to cause acute radiation syndrome in an unshielded human being in a matter of hours. One of those events in the wrong moment on a Mars transit could be a catastrophic emergency. And there's no reliable way to predict them more than about 15 to 60 minutes before they arrive. That's about as much warning time as a fast-moving tornado. Except tornadoes don't fry your bone marrow. But radiation from outside the solar system is almost more unsettling than the kind from our own sun because it's ancient. Some of those cosmic ray protons have been traveling across the universe for billions of years. They were launched by cataclysms that happened before our sun existed, before the Earth formed, before the first multicellular life appeared in our oceans. And they're still traveling, still carrying that energy, still arriving, passing through you right now. Every atom in your body was forged in a star, and the radiation hitting you right now was launched from other stars long before the star that made you was even born. That's not metaphor, that's physics. But cosmic rays, as frightening as they are at least something we understand. They're particles with energy. They follow rules. They interact with matter in ways we can measure and to some degree predict. What we're about to talk about next doesn't play by the same rules. And for a long time, we weren't even sure it was real. Chapter 3. The monster at the heart of everything. There is a thing in the universe that we cannot explain. Not in the sense that we haven't figured it out yet, like a puzzle we're still working on. In the sense that the closer we look at it, the less our current models of reality can account for it. It sits at the center of almost every galaxy we've ever observed. It is millions, sometimes billions of times more massive than our sun. It distorts space and time so severely that within a certain distance from it, the laws of physics as we understand them stop applying in any coherent way. And right now, in the center of our own galaxy, about 26,000 light-years from where you're sitting, there is one. We call it Sagittarius, a star. It has a mass of about 4 million times the mass of our Sun. 4 million suns compressed into a region smaller than our solar system. If you replaced our Sun with Sagittarius, a star, and kept all the planets in their current orbits, every one of them would still be orbiting the black hole comfortably. The event horizon, the point of no return, would sit somewhere inside Mercury's orbit. You'd need to be closer to it than Mercury is to our current Sun before you'd fall in. 4 million solar masses sounds like a big number. Here's what that means for your body at a specific distance. If you found yourself at about 80 kilometers from the event horizon of Sagittarius, a star, the difference in gravitational pull between your head and your feet would be strong enough to literally elongate you into a strand of atoms. Scientists call this process spaghettification, which is a word that contains dark comedy and genuine horror in equal measure. You wouldn't explode. You wouldn't burn. You would be drawn out into a thin thread of matter the way you might pull taffy, except the taffy is made of the atoms that were you, and it happens at a rate that would take about 1.3 seconds from person to strand. But here's what's even more disorienting than the physics of falling in. Black holes don't just crush matter. They crush the structure of space-time itself. Inside the event horizon, the mathematics of general relativity breaks down in a specific and deeply strange way. The dimension of time and the dimension of space swap their roles. Time, which flows forward for you in one direction no matter what, becomes a spatial dimension. And one of the spatial dimensions, the one pointing toward the singularity, becomes the direction of time, meaning that inside the event horizon, moving toward the singularity isn't moving through space. It's moving through time. And you can no more stop yourself from falling toward the singularity than you can stop yourself from aging. You would have no choice but to reach it, because not reaching it would require you to go backward in time. Let that sit for a moment. The singularity at the center isn't a place you move toward. It's a time you age toward. It's your future. And it is a future that physics, as we currently understand it, cannot describe. Our best equations literally produce infinities at that point, not big numbers. Actual mathematical infinities, which is physics's way of saying, we don't know what happens here. Our model of reality stops working before you get there. We discovered that Sagittarius, a star, underwent a significant brightening event in 2019, suddenly flaring to over 75 times its usual brightness before returning to its baseline. The cause isn't fully understood. Something got close enough to disturb it. Maybe a star. Maybe a gas cloud. Maybe something we haven't categorized yet. The black hole at the center of our galaxy is not dormant. It is not dead. It breathes. And that brings us to the part that should make you put your phone down for a second to think. Because right now, we are 26,000 light-years from Sagittarius, a star. That's about 246 quadrillion kilometers. Imagine the entire distance from Los Angeles to New York City reduced to the width of a single human hair. On that scale, the distance to Sagittarius, a star, would still be wider than a standard doorway. It is genuinely, inconceivably far away. But the Milky Way isn't staying still, and neither is anything else in the universe. Chapter 4. Everything is falling, and nobody knows where. In 1986, a group of astronomers noticed something that didn't make sense. Galaxies. Clusters of galaxies, enormous structures containing hundreds of trillions of stars, were all moving in a direction they shouldn't be moving based on the known distribution of matter in the universe. It was as if something was pulling them. not a gravitational nudge. A sustained, massive directional drift. Whole galaxy clusters, each one containing more stars than there are grains of sand on every beach on Earth, all flowing toward a single point in the sky. Astronomers named that point the Great Attractor. And here's the part that made them particularly uncomfortable. We're in it. The Milky Way is one of the galaxies being pulled toward the Great Attractor right now. We are drifting toward it at a speed of about 630 kilometers per second. That's fast enough to travel from the surface of the Earth to the Moon in about 10 minutes. Not driving. Not flying. 10 minutes. That's our drift speed towards something we cannot fully see. Why can't we see it? Because it happens to sit in the direction of the Milky Way's central disk, which is packed with so much dust and gas that optical telescopes can't see through it. We are being pulled towards something enormous that our primary means of observation cannot penetrate. It took X-ray and radio observations to start piecing together what's there. What we've found is a structure of truly stupefying scale called the Laniakea supercluster, which is a collection of about 100,000 galaxies spanning roughly 520 million light-years from one end to the other. If you took the entire observable universe and shrunk it to the size of a basketball court, Laniakea would still be about as wide as a dinner plate on that court. It's an almost incomprehensible web of galaxies and dark matter filaments, and its mass is so great that it influences the motion of everything inside it. Our galaxy is not free. It has never been free. It's been caught in this gravitational web since before our solar system formed. And within that web, things collide. In roughly 4.5 billion years, our Milky Way will collide with our nearest large neighbor, the Andromeda Galaxy, which is currently about 2.537 million light-years away. But it's approaching at about 110 kilometers per second. That's every second. At that rate, if Andromeda were a car and you were standing a mile away, it would reach you in about 15 seconds. The merger won't destroy the solar system outright because the distances between stars are so enormous that actual collisions between individual stars are unlikely during a galactic merger. But it will completely restructure the orbits of both galaxies over a period of hundreds of millions of years. The combined result, which astronomers have already modelled, is a new galaxy that cosmologists have nicknamed Milkdromeda. Our night sky over those hundreds of millions of years would look like something from a science fiction film as the spiral arms of Andromeda rise over the horizon like a second galaxy painting the dark. Whether anything lives to see that is another question, and it connects to something so disturbing that we almost didn't include it. Chapter 5. The bullet that almost killed everything. On the 27th of December 2004, Earth was hit by the largest burst of energy from outside our solar system ever recorded affecting Earth in the modern era of detection. A magnetar, which is a type of neutron star with a magnetic field so intense that if one existed at the distance of the Moon from us, it would erase the magnetic stripe on every credit card on the planet, experienced what's called a starquake. The crust of this neutron star, which is harder than any material we've ever created, and sits on a ball of matter so dense that a teaspoon of it would weigh about 10 million metric tons, roughly the mass of 2 million elephants, cracked. Just slightly. A crack that released, in a fraction of a second, more energy than our Sun produces in 100,000 years. The magnetar was called SGR 1806-20, and it sat about 50,000 light-years from Earth. That's halfway across our own galaxy. And even from that distance, the gamma-ray burst it produced when its crust cracked was powerful enough to partially ionize our upper atmosphere and measurably disturb Earth's ionosphere. It affected the behavior of radio signals around our entire planet. From 50,000 light-years away. Here's how to feel that number. If you started reading this script out loud at a comfortable pace and kept reading, Without sleeping, eating, or stopping, you would finish around the 2-hour mark. Now imagine that the time between each of your words was extended, not by a minute, not by a year, by 1,000 years. So the first word takes 1,000 years to finish, then silence for another 1,000, then the next word. You would finish reading this script in about 50 million years at that pace. The magnetar that nearly ionized our atmosphere was farther from Earth than that seems long, and it still affected us. Now, there are two things that kept this from being a mass extinction event. First, the burst lasted only about 0.2 seconds at peak intensity. Second, the beam of energy wasn't perfectly aimed at us. We caught a glancing blow from the gamma rays, not the full force. But the universe contains events that would not give us a glancing blow. A gamma ray burst from a collapsing massive star, which is called a long gamma ray burst, produces 2 jets of gamma radiation that extend in opposite directions for light years. These jets are so concentrated and energetic that if Earth were caught within the beam path of a nearby one, meaning within a few thousand light years, the gamma rays alone would strip away the ozone layer on the side of Earth facing the burst. Not damage it, strip it. The planet's surface on that side would be exposed to the full radiation of the sun's ultraviolet output with no atmospheric protection within minutes. Photosynthesis would collapse. The food chain would follow. The mass extinction would follow that. We have evidence this may have already happened. There is a leading hypothesis, supported by analysis of the pattern of marine extinctions in the fossil record, that the late Ordovician mass extinction event about 443 million years ago, which killed roughly 85% of species in the ocean, may have been triggered by a gamma ray burst from somewhere in the Milky Way. Think about that. 85% of ocean species gone. Possibly because a star died too close to us, pointed slightly in our direction, and lit the sky for a fraction of a second. The universe killed 85% of ocean life in one momentary flash from a star that was already dead before its light reached us. And here's what keeps astronomers up at night. We don't know when the next one in our vicinity will fire. We can observe gamma ray bursts happening in distant galaxies, several detected every day from telescopes like the Neil Gehrels Swift Observatory. We can see them happening in other galaxies constantly. We cannot predict when one will happen near enough to matter to us. Our galaxy, the Milky Way, produces them at a statistical rate estimated between 1 and several per million years. 1 per million years sounds low. Humanity has existed for about 300,000 years. So statistically, roughly 1 could have occurred in a galaxy close enough to matter in that window. We just don't know. And we cannot stop it, predict it, or shield against it with anything we currently have or can envision building. It would happen at the speed of light, which means by the time we saw it coming, it would already be here. That's not the strangest part though, not by a significant margin, because the next thing we need to talk about makes gamma ray bursts look like something we could at least conceptually prepare for. Chapter 6. The darkness between the light. You've heard of dark matter. Maybe you've nodded along when someone explained it. Maybe you accepted the explanation that it's just invisible stuff we can't see but we know is there. But do we know what it is? That's the question we need to sit with for a moment, because the honest answer is no. And that no is far more unsettling than most popular science communication admits. Here's what we know. The visible matter in the universe, every star, planet, gas cloud, and nebula that we can detect using light or any part of the electromagnetic spectrum, makes up about 5% of the total mass energy content of the universe. About 27% appears to be dark matter, stuff that has mass and therefore gravitational effects but emits, absorbs, or reflects no electromagnetic radiation whatsoever. And about 68% is dark energy, which is even more mysterious, and we'll get to that. We know dark matter exists because of what it does. Galaxies rotate in a way that makes no sense if they only contain the visible matter we can see. The stars at the edges of galaxies orbit at speeds that should fling them out into intergalactic space, because there isn't enough gravitational mass in the center to hold them at those velocities. But they don't fly off, they stay. Which means there's mass we can't see, surrounding the visible galaxy like an invisible halo, providing the gravitational scaffolding that holds everything together. Every galaxy we've ever looked at has this. Every single one. The visible universe is essentially a thin coating on the surface of a much larger, invisible structure made of dark matter. We have never detected a dark matter particle directly. Billions of dollars have been spent on experiments designed to catch one. Underground laboratories built in old mines to shield detectors from cosmic ray interference. Tanks of xenon kept at temperatures colder than the surface of Pluto, which is about -229 degrees Celsius, colder than a place you'd need to dress very warmly to survive in, making space-grade cold look modest in comparison. Sensitive instruments specifically designed to feel the tiny recoil of a dark matter particle bouncing off an atomic nucleus. Nothing. Not a confirmed detection anywhere. The leading theoretical candidate for years was called a WIMP, which stands for Weakly Interacting Massive Particle. The theory predicted that particles of this type would interact with ordinary matter just often enough that our detectors should be catching them. But experiment after experiment has failed to find them. The region of parameter space where WIMPs were predicted to live has been searched exhaustively and is largely ruled out now, which means one of two things. Either dark matter is made of something that interacts with ordinary matter even more weakly than WIMPs were predicted to, making it even harder to detect. Or our model of what dark matter is fundamentally wrong. And we need to go back to the beginning. Either answer is deeply strange. Because if dark matter interacts so weakly with regular matter that we genuinely can't detect it even with our best instruments, then trillions of dark matter particles pass through you every second. Through your body. Through the Earth. Through the Sun. Without touching anything. Without leaving a trace. A universe running parallel to ours in some sense, occupying the same space, influencing everything through gravity, and completely invisible to any instrument we can build. 27% of the universe is made of something we have never once detected. But dark energy is stranger still. Because dark matter at least has mass. At least it behaves like something. Dark energy doesn't behave like something. It behaves like the rules of physics have a footnote nobody told us about. Chapter 7. The force that is ending everything. In 1929, Edwin Hubble showed that the universe is expanding. Galaxies are moving apart from each other, not because they're flying through space, but because space itself is stretching. Imagine the universe as a balloon and the galaxies as dots on its surface. As you inflate the balloon, the dots don't move across the surface. The surface between them grows. That's what's happening to the universe. Everyone understood this. And everyone assumed that over time, gravity would eventually slow the expansion down. Maybe reverse it into a big crunch. Maybe just slow it to a coast, but decelerate it. In 1998, two independent teams of astronomers were using Type Ia supernovae as distance markers, which work because these specific types of stellar explosions have a known intrinsic brightness, so you can calculate how far away they are by how bright they appear. They were measuring the expansion rate of the universe throughout its history by looking at supernovae at different distances, meaning different points in cosmic time. They expected to find that the expansion was slowing down. They found the opposite. The expansion is speeding up. The universe is not just expanding, it's accelerating. The rate at which space is stretching is increasing over time. This was so unexpected that both teams assumed they'd made an error. They spent months checking their data. Other teams checked it. The result held. In 2011, the scientists who led those teams won the Nobel Prize in Physics for the discovery. But what's causing it? We don't know. Whatever it is, we call it dark energy, and it seems to be a property of space itself. Empty space has energy. And the more space expands, the more of this dark energy there is, which accelerates the expansion further, which creates more space, which creates more dark energy. Think of it like compound interest, except instead of money growing in a bank account, it's the universe growing against itself. And the debt being paid is the future existence of every galaxy, star, and planet within it. Here's what this means over cosmological time. Right now, there are galaxies we can observe that are already accelerating away from us faster than light, not traveling through space faster than light. That's not possible. But space between us and them is expanding so rapidly that the distance is growing faster than light can cross it, which means those galaxies are already unreachable. Not difficult to reach, unreachable in principle, forever. Any signal we sent would never arrive. Over billions of years, more and more galaxies will cross this threshold. Our observable universe, the bubble of space we can in principle see and interact with, will shrink. Not because we're moving, because the edges are receding faster than information can travel. Galaxies that are currently visible to us will, one by one, redshift into invisibility and then beyond communication, and eventually beyond detection of any kind. In about 100 billion years, the only galaxies left in our observable universe will be the handful bound to us by gravity tightly enough that dark energy can't pull them away. Everything else will have vanished beyond our horizon. A civilization that evolved in 100 billion years, if one could exist, would look out at a universe that seems to contain nothing but a small local group of galaxies. They would have no evidence that billions of other galaxies ever existed. They would have no way to deduce the Big Bang, no way to discover the true nature of the cosmos. The information would simply be gone. We are lucky to exist now. At this particular moment in the 13.8 billion year history of the universe, when the cosmic microwave background radiation that carries the fingerprint of the Big Bang is still detectable, when distant galaxies are still visible, when the universe can still be read like a book by those who know how. In 1 trillion years, that book will be blank, and nothing will be alive to try to read it. But that 1 trillion year scenario isn't even the most immediately terrifying consequence of dark energy, because the current best understanding of its behavior implies something far more immediate for the physical structure of reality. And this is the part that produced genuine, sustained, not casual alarm in the physics community when it was first rigorously examined. Chapter 8. The End of All Things and Why It Might Be Soon. There's a scenario in cosmology called vacuum decay, and it may be the most haunting thing ever described in the language of physics. To understand it, you need to understand that the vacuum of space isn't actually empty. Quantum field theory, which is the most precisely tested theory in the history of science, describes the vacuum as seething with quantum fluctuations, virtual particles popping in and out of existence, fields with specific energy levels threading through all of space. And those energy levels matter. The Higgs field, which is the field associated with the Higgs boson discovered at CERN in 2012, gives all matter its mass. It permeates all of space, and it exists in a specific energy state. The question physicists have been wrestling with is whether the Higgs field is in its true lowest energy state, which they call the true vacuum, or whether it's in a false vacuum, an energy state that's stable but not the absolute minimum, like a ball resting in a dip on a hillside rather than at the very bottom of a valley. When scientists measured the mass of the Higgs boson at about 125 billion electron volts, and combined that with measurements of the top quark mass, calculations indicated something deeply uncomfortable. the Higgs field appears to be metastable, meaning it's in a false vacuum. It's stable enough to have lasted 13.8 billion years, but it may not be stable forever. If the Higgs field were to tunnel to a lower energy state, it would create a bubble of true vacuum. This bubble would expand outward at exactly the speed of light in all directions. As it expanded, the laws of physics inside the bubble would be fundamentally different from the laws of physics outside it. Different constants, different masses for particles, a different structure of reality itself. And every atom of matter that the bubble wall encountered would be instantly reconfigured into something else. Not destroyed in the sense of energy being released. Reconfigured. The electrons and protons that make up atoms would find themselves in a universe where they couldn't be electrons and protons anymore. The bubble wall would travel at the speed of light. You would have no warning. There is no warning possible. The first information that the bubble existed would be the bubble wall itself. And you would not experience it. Not even for a fraction of a second. Because everything in your body would be reconfigured into something that couldn't process experience before any signal could propagate from one neuron to another. One moment you're here. Then you're part of a different universe where the particles that were you follow different rules and mean nothing of what they meant before. The entire observable universe could be consumed this way. Every galaxy, every star, every planet, everything that has ever been alive anywhere in the cosmos. All of it remade in a bubble that started somewhere with a random quantum fluctuation that nobody chose and nobody caused. It could have already started, right now. Somewhere out there, a bubble of true vacuum could be expanding towards us at the speed of light, and we will have zero warning before it arrives. Now, here's the genuinely complicated part of this. The current calculations suggest our universe is either in the true vacuum or in the metastable false vacuum with an extremely long lifetime before any spontaneous transition. Meaning this scenario is possible potentially, but the timescale, if it happens at all, could be far longer than the current age of the universe. Physicists estimate the metastable vacuum lifetime could be somewhere between 10 to the power of 100 years and literally infinite, which means it might never happen. But the fact that it can't be ruled out. The fact that the Higgs field measurements put us in a region of parameter space where the answer is maybe, and we can't tell you more precisely than maybe, is one of the things that keeps cosmologists staring at their office ceilings at 2 a.m. Maybe. In the physics of existence. Maybe is not a comfortable answer. But vacuum decay is a maybe. What comes next is not. Chapter 9. The Dark Forest and the Silence That Screams. In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory, and the conversation turned to UFOs and the possibility of extraterrestrial intelligence. Fermi thought for a moment and asked a question that has haunted science ever since. Where is everybody? The Milky Way is about 13.5 billion years old. It contains somewhere between 200 and 400 billion stars, with estimates of that number shifting upward with each new survey. A large fraction of those stars have planets. Many of those planets are in what we'd call the habitable zone. The conditions for life, at least as we understand them, should exist in thousands, possibly millions of locations within our galaxy alone. Even if life only arises on 1 in a billion planets, that's still potentially hundreds of civilizations just in the Milky Way. And if any of them develop technology even a few million years before us, which on the timescale of the galaxy is the blink of an eye, they would have had time to spread their influence, their signals, their machines across the entire galaxy many times over. And yet, silence. We've been listening for radio signals from other civilizations since 1960 with SETI, the search for extraterrestrial intelligence. We've scanned millions of stars. We've detected nothing that holds up as a confirmed alien signal. In over 60 years of searching, in a galaxy that should be brimming with civilizations if the Drake equation and our understanding of planetary habitability is anywhere near correct, we've heard nothing. This is the Fermi paradox. And every proposed solution to it is disturbing in its own specific way. Maybe intelligent life is actually incredibly rare, and we're genuinely alone, or nearly alone. This is called the rare Earth hypothesis. If true, it means the gulf of space that looks terrifying from the outside is even more isolating than it appears. We may be the only voices in an otherwise silent cosmos. The weight of that silence, if real, is something that resists description. Maybe intelligent life tends to emerge and then disappear, for reasons we haven't discovered yet. The Great Filter Theory suggests that somewhere in the progression from simple chemistry to spacefaring civilization, there is a step that almost nothing makes it through. A catastrophic failure that resets the experiment. Every time. Almost everywhere. The terrifying question is, have we already passed that filter, or is it still ahead of us? If the filter is behind us, if the fact of eukaryotic cells, or sexual reproduction, or multicellular life is itself the unlikely step, then we might be the rare exception that made it through. We're special. We're the lucky ones. The universe is mostly dead, and we survived what almost everything else didn't. But if the filter is still ahead of us, if the catastrophic failure mode happens to civilizations after they reach our current level of development, well, we're about to find out what it is, firsthand. Maybe the silence isn't emptiness. Maybe it's strategy. The dark forest hypothesis, named after a science fiction novel by Liu Cixin, but based in actual game theory logic, proposes that any sufficiently advanced civilization would choose to remain silent precisely because the universe is so dangerous. If you announce your presence, any other civilization that hears you has to make a calculation. You might be a threat. Resources are finite. The safer choice, from a purely logical standpoint, is to eliminate you before you become a problem. In this framework, the universe isn't empty. It's full, and everything in it is silent, hiding, listening, waiting to see if anyone makes the mistake of speaking. We've been broadcasting our presence since the first radio waves left Earth about 120 years ago. Those waves are currently in an expanding sphere around our solar system, moving outward at the speed of light. The nearest stars already know we're here. They've already seen our first TV broadcasts, our early radar pulses, our radio noise. That signal bubble, our announcement of existence to the cosmos, now spans about 240 light-years in every direction. A sphere of disclosure we sent without realizing it, long before we understood the full weight of what we were doing. Whether the dark forest is real or paranoid fiction, the point it makes about the universe is worth sitting with. We have never once been guaranteed safety. We live in a cosmos where the default state of stars is explosion, the default state of black holes is annihilation, the default state of most of space is radiation and vacuum, and temperatures near absolute zero, which is about negative 273 degrees Celsius. And even the fabric of space-time itself might one day rewrite the rules of existence without warning. We've built civilization inside a dangerous universe, and we've done it without knowing if we were ever truly alone in here. Chapter 10. The neighbors we didn't know about. Here's one that doesn't make enough headlines. In 2023, using data from the Microlensing Survey Network and the Gaia Space Telescope, astronomers revised upward the estimated number of rogue planets in our galaxy. A rogue planet is exactly what it sounds like. A planet with no star. no solar system. Just a world, wandering alone through interstellar space in complete darkness. The current best estimate is that there could be roughly 20 billion rogue planets in the Milky Way. Some estimates go higher, reaching 50 billion. That's potentially more free-floating planets than there are stars. Worlds with no sun, no warmth, no light, hurtling through the darkness between the stars at speeds of tens of kilometers per second. Most of them are cold. Surface temperatures near absolute zero. Dead things in the dark. But not all of them. Some rogue planets are large enough, specifically super-Earths and above, to retain internal heat from their formation through radioactive decay in their cores, similar to how our Earth's interior is kept warm. Some could have thick hydrogen atmospheres that act as greenhouse blankets, trapping geothermal warmth beneath a permanent overcast sky. Some might even have liquid water, deep below the surface, warmed by tidal forces if the planet has a moon, or by the ongoing radioactive decay of elements in the mantle. None of this means rogue planets are inhabited. The evidence for that doesn't exist. But the point isn't about life. The point is that there are billions of worlds out there we didn't know about even a decade ago, wandering the darkness of the galaxy. And some of them are large enough and have been drifting long enough that they could theoretically intersect a solar system, including ours. Now, the probability of a rogue planet encountering our solar system in the next several billion years is genuinely very low. The galaxy is big enough that even with 20 billion rogue planets drifting through it, actual close encounters are statistically rare. But rare in cosmic timescales can mean once every billion years. And once is enough. In 2017, we detected the first confirmed interstellar visitor to our solar system. It was a small object, maybe 400 meters long, the length of about 4 American football fields, tumbling end over end as it passed through, and we named it Oumuamua, from the Hawaiian term for scout or messenger. It was moving too fast to have originated from our solar system. It came from interstellar space, passed through and left. And it had a shape unlike any asteroid or comet we'd seen before. So unusual that several scientists, including Avi Loeb of Harvard, raised the controversial and majority-rejected possibility that it might have been artificial. It almost certainly wasn't. But the fact that we detected it matters, because it was the first confirmation that interstellar objects pass through our solar system. And if small objects pass through, larger ones can too. The universe is not a museum. It's not a static display. It's a dynamic, violent, constantly churning environment where things move, collide, explode, and drift into unexpected places. And we're sitting inside it in a comparatively tiny bubble of warmth and stability, hoping the next thing to drift through stays far enough away. Chapter 11. Neutron stars and the matter that shouldn't exist. We've mentioned neutron stars in passing. But they deserve their own moment because they are perhaps the clearest example of the universe doing something that seems to violate our intuitions about what matter even is. When a star between about 8 and 20 times the mass of our Sun runs out of fuel and collapses, the outer layers explode outward in a supernova. The inner core, however, collapses inward. Gravity crushes it so intensely that electrons are forced into protons, converting them into neutrons. The core collapse happens in about 1/10 of a second. In that 1/10 of a second, something the size of the Earth is compressed to an object about 20 kilometers across, roughly the size of a major city. And all the energy released in that collapse, more than the Sun will radiate in its entire 10 billion year lifespan, is released in those few seconds in the form of neutrinos, tiny neutral particles that barely interact with anything. The resulting object is a neutron star. All those neutrons packed together under gravity so intense that matter as we know it ceases to apply. A teaspoon of neutron star material would weigh about 10 million metric tons. Imagine a teaspoon that weighs the same as roughly 2 billion people stacked on a single spoon. That's neutron star density. The surface gravity of a neutron star is about 200 billion times Earth's gravity. If you could somehow stand on the surface of a neutron star, the gravity pulling you down would be so extreme that if you tripped and started falling from a height of just 1 centimeter, which is less than the height of a standard coat button, you would hit the surface at about 7 million kilometers per hour. And you would not bounce, no. The magnetic fields of neutron stars are almost beyond comprehension. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. A magnetar, the subcategory we mentioned earlier with the 2004 flare, can have fields 1,000 times stronger than that. The magnetic field of a magnetar at the distance of the moon would be strong enough to pull the iron out of your blood. Not metaphorically. The iron ions in your hemoglobin would be magnetically attracted to the source. Your blood would behave like a paramagnetic fluid responding to a powerful external field. Whether you could survive that or not is something no one has ever tested for obvious reasons. And yet, for all their exotic horror, neutron stars might actually be something like neighbors. When two of them collide, and we detected one such collision using gravitational waves in August 2017, the event is called a kilonova. Kilonovae are now believed to be the primary source of heavy elements in the universe. Elements like gold, like platinum, like uranium. The gold in your wedding ring, if you have one, was forged in the collision of 2 neutron stars somewhere in our galactic history. Your jewelry is the remnant of a cosmic catastrophe. The universe gave us the beautiful and terrible in the same event. That seems right. Chapter 12. The thing that shouldn't exist but does. In 2015, the Laser Interferometer Gravitational Wave Observatory, which we call LIGO, detected something that Einstein predicted should exist but that many physicists doubted we'd ever actually observe. Gravitational waves. When 2 massive objects orbit each other and spiral together, they warp space-time around them, and those warps propagate outward as waves. Like ripples on a pond, except the pond is the fabric of space-time itself, and the ripples travel at the speed of light, and they stretch and compress literally everything they pass through. The first detection was the merger of 2 black holes, 1.3 billion light-years away. That event released more energy in a fraction of a second than every star in the observable universe combined emits in the same time window. All of it in the form of gravitational waves. And when those waves reached Earth after traveling for 1.3 billion years, which is to say they left when the most complex life on Earth was single-celled organisms in shallow Cambrian seas, the waves physically stretched and compressed the 4-kilometer arms of the LIGO detector by a distance of 1,000th the diameter of a proton. 1,000th of a proton. That's the signal. That's what we detected. An instrument sensitive enough to measure space-time deformation at a scale that makes a proton look enormous, triggered by a collision that happened over 1 billion years ago. And we measured it. We built a machine that does that. Humans did that. There's something about that which feels important to hold on to. Not just the terror of the universe, which is real and documented throughout this script, but the fact that we built LIGO. That we solved quantum mechanics and general relativity. That we looked at the Hubble images of galaxies hundreds of millions of light years away and said, we want to understand what that is. That impulse, that compulsive need to understand, might be the most specifically human thing about us. Because the universe didn't give us understanding. It didn't give us safety or warmth or shelter. It gave us the conditions for complex chemistry, and we did the rest. And in a cosmos where 95% of the content is invisible to us, where black holes eat time, where the entire fabric of reality might reset itself without warning, where gamma-ray bursts can strip atmospheres and rogue planets drift in the dark between stars, and where we have been searching for decades for anyone else in this vast machine and heard only silence, there is something both humbling and deeply moving about the fact that we keep asking. We keep looking. We keep building detectors and telescopes and equations. We keep pointing cameras at the dark, not because we expect it to be safe out there. We know it isn't. But because the alternative, to stop looking, to decide the universe is too big and too dangerous to try to understand, feels worse than the fear. Chapter 13. What the James Webb Space Telescope found that nobody talked about enough. In 2022 and 2023, the James Webb Space Telescope began returning data, and some of what it found immediately created tension with our best models of how the universe evolved. Webb was designed to look at the early universe to see galaxies forming in the first few 100 million years after the Big Bang. What it found was that there are fully formed, massive galaxies in the very early universe that, according to our current models of galaxy formation, should not be there. Not shouldn't be there in the sense of being surprising. Shouldn't be there in the sense of not having had enough time to form. These galaxies are so massive and they appear so early in cosmic history that the current leading model of how dark matter structures form and how galaxies grow within them, called lambda CDM, struggles to account for them. Some of these early massive galaxies have more stars than our entire Milky Way, and they appear to have assembled in a fraction of the time our models predict such assemblies should take. This might mean we're missing something in our understanding of dark matter behavior. It might mean star formation in the early universe was significantly more efficient than we thought. It might mean the expansion history of the early universe was different from what the standard model predicts. Or it might mean something more fundamental, that there's a piece of physics we simply haven't discovered yet, something that operates at the intersection of quantum mechanics and gravity, a regime where our two best theories of the universe currently refuse to shake hands and agree on anything. General relativity describes gravity and the large-scale structure of the universe with extraordinary precision. Quantum mechanics describes the subatomic world with extraordinary precision. When you try to combine them, the math breaks. They contradict each other in ways that matter enormously at scales like the interior of a black hole or the first instant of the Big Bang, and possibly at scales that the early Webb galaxy observations are pushing into. We do not have a theory of quantum gravity. We have candidates: string theory, loop quantum gravity, causal dynamical triangulation, and others. None of them have produced a confirmed, unique, testable prediction that distinguishes them from the others in a way that experiments have been able to resolve. The two best theories we have of the universe, the ones that between them account for virtually every observation and experiment in the history of physics, are mutually incompatible. At the deepest levels, we don't know how the universe actually works. And the James Webb images are beginning to probe those incompatible depths. Every new image it sends back is a postcard from a region of the universe's history where our models might be wrong. We're not just learning more. We're learning the shape of our own ignorance. And the shape is bigger than we thought. Chapter 14. The scale of the real. Let's return to something simple for a moment, because after everything we've covered, it's worth grounding ourselves in something concrete. You are made of atoms. About 7 octillion of them, which is a 7 followed by 27 zeros. If all those atoms were inflated to the size of blueberries and laid side by side, they would stretch for approximately 45 billion light years, which is slightly wider than the observable universe itself. You are, in a sense, a universe-sized amount of matter compressed into a human form. Every one of those atoms has existed since the Big Bang. Not the atoms themselves, which formed somewhat later, but the fundamental particles they're made of, the quarks and electrons. Those trace their lineage to the first microseconds of the universe's existence. They've been through stellar furnaces, through supernova explosions, through billions of years of cooling and reforming in nebulae, through the collapse of a dust cloud that became our solar system, through the chemical processes of the early Earth, through billions of years of biology. And now they're arranged in the specific configuration that is you, reading this, alive and aware. You are the universe knowing itself. You are atoms that somehow became curious about the other atoms they're surrounded by. That is not a small thing. In a universe that is 13.8 billion years old, in a galaxy that contains hundreds of billions of stars, on a small rocky planet orbiting an unremarkable star near the edge of one of the galaxy's spiral arms, matter organized itself into something that could build the LIGO detector and feel awe when it worked. That could look at a black hole and want to understand it rather than just flee from it. That could spend decades listening for a signal from the dark and feel the weight of the silence without giving up. The universe gave us no guarantees, no protection from its own violence, no whisper that we were expected or wanted or noticed. It gave us physics. The same physics that creates gamma-ray bursts and vacuum decay and neutron star magnetic fields also created the conditions for hydrogen to become helium, for helium to become carbon, for carbon to become you. The universe isn't hostile to us the way a predator is hostile to prey. It's indifferent in a much deeper way. It doesn't know we're here. It doesn't care. Its dangers aren't aimed at us. They just exist. And we exist inside them, temporarily on a planet with a protective magnetic field and an atmosphere thin as an apple's skin, watching from a safe enough distance to ask the questions. Whether that's beautiful or terrifying is a question only you can answer. Maybe it's both. Maybe both at once is the honest answer. Chapter 15. The last thing. There's one more thing we need to talk about. The final thing. And it's the quiet one. Not a gamma-ray burst, not a black hole, not vacuum decay. Something slower and, in its way, more complete. The universe is running down. The second law of thermodynamics, which is one of the most ironclad laws in all of physics, states that in a closed system, entropy, which is a measure of disorder, always increases over time. The universe is a closed system, and its entropy is increasing. Every star that forms eventually burns out. Every galaxy that shines will eventually exhaust its gas reservoirs and stop producing new stars. Every black hole, which seems so permanent and indestructible, will eventually evaporate through a quantum process called Hawking radiation, slowly losing mass by emitting thermal radiation until it's simply gone. This process takes incomprehensible lengths of time. A stellar mass black hole would take about 10 to the power of 67 years to evaporate. A supermassive black hole like Sagittarius. A star would take something like 10 to the power of 92 years. Compared to those timescales, the entire current age of the universe is so small it's essentially zero. But it will happen. Everything we see will eventually go dark. Every star will die. Every black hole will evaporate. And eventually, after timescales that make the age of the universe look like a heartbeat, the universe will reach a state of maximum entropy. A cold, dark, infinitely expanded state with no temperature gradients, no concentrations of energy, no complexity, no chemistry, no biology, no thought. Cosmologists call this the heat death of the universe. It's not that everything ends with a bang or a collapse or a reset. It ends by becoming perfectly still, perfectly uniform, perfectly quiet. Everything spread infinitely thin. Every gradient gone. No more events. No more time in any meaningful sense. Just emptiness at perfect equilibrium, lasting forever. We are living in the extraordinarily brief moment in cosmic history when the universe is young enough and energetic enough to support stars and planets and life. The universe is about 13.8 billion years old. The total timeframe of stellar evolution before the last stars die is estimated at about 100 trillion years. That's roughly 100 trillion years. We are currently not even 2/10,000ths of the way through the era of stars. And yet, on the scale of what comes after, even that era is nothing. The era of black holes that follows will last 10 to the power of 100 years. And the silence after that will last forever. We are a morning in a universe that has an inconceivably long night ahead of it. And somehow, in the middle of that morning, in the brief window when the laws of physics allow atoms to organize themselves into something curious, something we call life, built a telescope and pointed it at the dark, not because it made us safe, not because we had to, but because we wanted to know. Because the questions felt important even when the answers were terrifying. Because wonder and dread are sometimes the same feeling, and that feeling is the most specifically human response to the universe we live in. We are made of the same particles as everything out there. The same quarks, the same electrons, the same fundamental fields. The same dark energy pulling the cosmos apart is present in every cubic centimeter of the space between your cells. You are not separate from the universe. You are a piece of it that became temporarily aware of its own existence. And right now, in this moment, you know things about where you are that your ancestors couldn't have dreamed of. You know that you're on a rocky world orbiting an ordinary star at the edge of a spiral galaxy, in a supercluster being pulled by the Great Attractor toward a point in the universe we can barely see. You know that space contains things that could end everything in a fraction of a second, and that the fabric of reality itself might be metastable. You know that 95% of the universe is invisible to us, and that the laws of physics we've discovered don't fully agree with each other at the deepest level. You know that the universe is old and dark and mostly empty, and will eventually become more empty, and more dark and more still than anyone can fully imagine. And you're still here, asking about it. That's not nothing. In a cosmos this large, this old, this indifferent, the fact that something emerged from the dark matter and the quantum fields and the stellar nurseries and asked, "What is all of this?" might be the strangest and most specific thing the universe has ever done. The terror of space is real. Every fact in this video is real. But the asking, the questioning, the refusal to look away from even the most frightening answers, that's real too. And as long as there are minds to ask the questions, the morning lasts a little longer. But here's what we haven't answered, and it might be the most important question of all. If the universe is this old and the conditions for life have existed for so long and the great filter is real and it lies ahead of us rather than behind us, what is it? What kills civilizations before they reach the stars? Is it war? Is it climate collapse? Is it a gamma ray burst they didn't see coming? Or is it something we haven't imagined yet, a failure mode built into the structure of what it means to be intelligent life in a physical universe with the physics our universe has? Because if the filter is ahead of us, and we're approaching it right now, living through whatever the critical period is, then the silence of the cosmos isn't just empty and lonely and terrifying. It's a warning. One we've been receiving for decades, and one we're only just beginning to understand how to read. And if you want to go deeper on the question of whether we're alone in this universe and what the silence might actually mean for our future, that video is right here. Watch it next. Because what astronomers are finding in their most recent survey data changes everything about how we think about the Fermi paradox, and some of it only just came out. You need to see it,